Something in a Nanjing laboratory just started conducting electricity at 27.8 millisiemens per centimeter. Picture the material first, before the name. It is gray, it is poured into molds, it holds up buildings, and for over a century, engineers agreed it was only ever supposed to do one thing. In May of 2024, that agreement broke. Southeast University published a version of this material called a solid-state electrolyte that conducts ions fast enough to store real electrical charge while getting stronger, not weaker. You heard that right. This is not a theoretical projection. It is a peer-reviewed result published in the journal Research with the strength numbers sitting right next to the conductivity numbers. Let me tell you what that actually means in plain English. You know the feeling of a power outage rolling through your street while the building around you just sits there, structurally useless the moment the grid goes down. And that is just the beginning. The real surprise is not that this works, it is how they got it to work. If a wall doing double duty sounds worth 6 minutes, hit a quick like and subscribe so you catch the next one. By the end of this video, you will understand exactly how cement was engineered to store power without sacrificing an ounce of strength. You have stood in a blackout with a dying phone, surrounded by a building that could not do a single thing to help you. For more than a century, that helplessness was built into the material itself. Cement is the most consumed material on Earth after water, and for all that volume, engineers only ever asked it to do one job: hold weight. Not conduct, not store. Just stand there, silent and structural, while the actual work of generating and holding electricity happens somewhere else. In batteries, in wires, in devices bolted onto the building rather than part of it. There was a reason for that division, and it was not laziness. It was physics. Cement gets its strength from a dense, tightly bound crystal structure that forms as it cures. Push conductive material into that structure, metal fibers, carbon particles, ion-friendly polymers, and you open gaps in the matrix the crystals need to lock together. Add enough conductive material to make the cement useful as an electrical component, and you have also made it brittle enough to crumble under the load it was supposed to carry. Engineers had a name for this. They called it the strength-conductivity trade-off, and for decades it was treated as a wall, not a puzzle. You could have a wall that held your roof up, or a wall that carried a charge, not both. In 2023, a team at MIT gave that wall its first real dent. Led by researchers including Franz Josef Ulm and Admir Masic, they built a working carbon cement supercapacitor. Coin-sized samples, wired together, strong enough to power a small LED. It was a genuine breakthrough, and it proved something the field had assumed was impossible. Cement could store real electrical charge. But the samples were small. The structural integration into an actual load-bearing wall was still unresolved, and the trade-off that had defined the field for a century had been dented, not broken. Praise where it is due. And then the honest question of where the ceiling still sat. That question landed on the desk of a materials scientist named Wei Lin, working out of the Jiangsu Key Laboratory of Construction Materials at Southeast University in Nanjing. Lin was not trying to build a better battery. He was circling a narrower, stranger problem. Why does every attempt to make cement conductive treat strength and conductivity as enemies, when nothing in nature works that way? Bone conducts and bears weight. Bark conducts and bears weight. Lin's obsession, the thing his own team would later describe as the core of the research, was finding an architecture where those two properties reinforced each other instead of competing. Here's what most people get wrong about this kind of research. They assume the answer was a new chemical. It was not chemistry that cracked this wall, it was structure. And the structure Lin's team eventually landed on did not come from a materials science textbook at all. It came from paying closer attention to things that were never built by engineers in the first place. But that idea did not arrive fully formed. Before Lin's team found their answer, a handful of earlier attempts had already tried to solve the same puzzle, and every one of them had been quietly dismissed. Researchers before Lin had tried layered electrolyte designs of their own. Cement combined with cyanide-based polymer structures engineered in stacked sheets to try to force ions to move in an orderly direction instead of a random one. On paper, the idea was sound. In practice, the conductivity of these earlier layered designs came in roughly 2 orders of magnitude below what would eventually be needed for a real structural application. They said the same thing about these attempts that they had said about every prior effort in the field. Interesting chemistry, no practical future. We all know how that pattern usually ends. The dismissal was not unreasonable at the time. 2 orders of magnitude is not a rounding error. It is the difference between a curiosity and a component. But the direction those earlier researchers had stumbled onto was correct, even if their execution fell short. Order mattered more than composition. A cement structure that forced its internal architecture into layers rather than leaving it random behaved differently, even if nobody had yet found the right material to fill those layers with. Lin and a close collaborator, Yang Zhou, made a decision that broke from where the rest of the field was looking. Instead of hunting for a new polymer chemistry, they turned toward biomimicry, toward materials that had already solved the strength and function problem outside a laboratory entirely. Nacre, the iridescent inner layer of a seashell, is nearly 3,000 times tougher than the mineral it is made from, purely because of how its layers are stacked. Sedimentary rock holds enormous compressive loads for the same structural reason. If cement's layers could be organized with that kind of precision, strength and conductivity might stop competing and start reinforcing each other. The mechanism they needed was not going to come from a chemistry set, it was going to come from ice. Here is the part that changes everything. Lin's team did not add a new material to force cement into layers. They used the water already inside the mixture and froze it on purpose. Picture a window pane in winter. Frost does not form randomly across the glass. Under the right conditions, it grows in clean, parallel lines, following the direction of the cold. That is the everyday version of what Lin's team engineered inside wet cement. As the cement began to cure, they applied a bidirectional temperature gradient across the mixture. Cold pushing in from one direction, forcing the water inside the slurry to freeze into oriented ice sheets rather than a random block of ice. As those ice sheets grew, they physically pushed the cement particles out of their path, herding them into thin, aligned layers stacked one on top of another. This is the exact structural puzzle Lin had been circling for years. Not a stronger chemical bond, but a more disciplined internal geometry. Once the layered cement structure had formed and hardened around the ice, the team sublimated the ice away entirely. The same freeze-drying process used to preserve food, just applied here to sculpt architecture instead of shelf life. What was left behind was not solid cement anymore. It was ordered cement, riddled with a network of clean, aligned microchannels running through it, like the rings inside a tree trunk. An internal structure that used to be random was now organized on command. That organization alone did not make the material conductive. The channels Lin's team had carved were empty, precise, aligned, and electrically useless on their own. A structure without a purpose is still just a structure. The layers were the architecture. They were not yet the function. That gap, a beautifully organized cement skeleton with nothing running through it, was the open problem staring back at Lin's team once the ice was gone. And the way they solved it is the part of the story that sounds like it should not work at all. Here is the brutal catch nobody in the field wanted to face. Filling those channels with anything conductive was supposed to weaken the whole structure again. That was the entire century-old trade-off. You open the material up to let ions move, and the crystal matrix that gives cement its strength stops locking together properly. Lin's team was staring at the same wall that had stopped everyone before them. Their answer was to stop treating strength and conductivity as separate problems that needed separate solutions. What if the exact channel carrying the charge was also the channel reinforcing the structure? That question is the paradigm break at the center of this entire breakthrough. Instead of injecting a soft, purely conductive filler into the ice-carved channels, the team filled them with a PVA-KOH hydrogel, a polymer-based gel engineered to do 2 jobs inside the same physical space: conduct ions rapidly along the aligned channels and mechanically bond with the surrounding cement lamellae like reinforcing bar running through concrete. It sounds like it should not work. A soft, water-based gel is not supposed to make a brittle mineral structure stronger. That is exactly why it does. Bonded into the aligned channels rather than scattered randomly through the material, the hydrogel behaved less like a weak point and more like connective tissue, holding adjacent layers together under load while simultaneously giving ions a fast, dedicated path to travel. The measured results, published alongside the mechanism itself, are what made the rest of the field pay attention. The finished material, Lin's team named it LCPSSE, showed a specific bending strength 2.2 times that of traditional cement and a specific compressive strength 1.2 times higher. At the same time, its ionic conductivity reached 27.8 millisiemens per centimeter. outperforming most previously reported cement-based and hydrogel-based electrolytes on record. For the first time, the same architecture that made the material stronger was the architecture that made it conductive. Mechanisms working in a lab sample under controlled conditions is one kind of proof. Scaling that same architecture into something that behaves like an actual building material is an entirely different problem, and it is the problem Lin's team had to solve next. A single conductive channel proves a concept. A building needs something else entirely. A coordinated system where thousands of those channels behave predictably at once under real structural load while still doing their job as an electrical component. Here is the detail that puts everything into perspective. A conventional cement electrolyte, even a good one, is engineered like a component bolted onto a wall, something added after the fact to give a structure a function it was never designed to have. Lin's team built something closer to a nervous system. The ice-templated layers and the hydrogel-filled channels were not treated as an add-on to the cement. They were the cement, integrated at the point of formation rather than injected afterward. Think of it the way a dedicated traffic lane works during rush hour. Cars moving through mixed traffic get stuck behind slower vehicles taking unpredictable, inefficient paths. Give that same traffic a straight, dedicated lane, and it moves faster and more predictably. Not because there are fewer cars, but because the path itself has been organized. That is what the ice templating process does for ions inside LCPSSE. It turns a random, congested path into a dedicated one, at the scale of the entire material rather than a single sample. This is the architecture Lin's team designed with a specific end goal in mind, one stated directly in their published research: enabling what the field calls zero-energy buildings, structures capable of generating and storing meaningful amounts of their own power, using the material that is already holding them up. Not a battery pack mounted on a wall, the wall itself, doing the work. For the first time, a cement-based electrolyte was designed from the start to be both the skeleton and the circuitry of a building rather than one or the other. A result this unusual, in a field this skeptical, does not get taken at face value from a single number. It gets checked, rechecked, and published only once the strength data and the conductivity data can stand next to each other without contradiction. That verification is exactly what happened next, and it is where this story stops being promising and starts being proven. Here is the honest picture. What Southeast University published in May of 2024 is a certified, peer-reviewed material breakthrough, not yet a finished deployable wall you could buy today. The certified numbers stand on their own. A specific bending strength, 2.2 times that of ordinary cement. A specific compressive strength, 1.2 times higher. An ionic conductivity of 27.8 millisiemens per centimeter, surpassing most previously reported cement-based and hydrogel-based solid electrolytes, published in the journal Research with the full methodology alongside it. The exact kind of scrutiny that separates a certified result from a press release. Translate that into something you can picture. A structural component that used to have to choose between holding weight and holding a charge no longer has to choose. In practical terms, that is the difference between a wall that is purely deadweight and a wall that participates in the building's own power system, storing energy the way a battery would without giving up the strength a wall is supposed to have in the first place. Now, the trade-offs, stated plainly rather than buried. This is a solid-state electrolyte. One essential component of a working structural supercapacitor, not yet a complete, weatherproofed, code-approved wall system ready for a construction site. Full-scale manufacturing, long-term durability under real humidity and temperature swings, and cost parity with ordinary cement remain open engineering problems. The same category of hurdle MIT's own team is still working through with sealants and scale-up on their version of this idea. The honest picture does not diminish the result. It is what makes the result credible. For Wei Lin, the number is not just a data point. It is the answer to the exact bet he made when he turned away from pure chemistry and toward biomimicry, proof that a wall genuinely did not have to choose between strength and function. If a wall storing its own power surprised you, the next part of the story is going to be even harder to believe. Hit subscribe so you are there when we cover it. Because if this material scales, the wider implications go well beyond one lab in Nanjing. Buildings account for roughly 30% of global final energy consumption and more than half of global electricity use, according to the International Energy Agency. That is the scale of the problem a material like LCPSSE is aimed at, not a niche application, but one of the largest energy sinks on the planet. The sectors this touches are broad: construction firms looking for structural materials that do more than sit there, renewable energy operators looking for distributed grid-edge storage that does not require dedicated battery installations, retrofit and building code industries already pushing towards zero energy standards, hunting for materials that can help a structure meet those targets without bolting on additional hardware. Engineers who worked on this will tell you the public reporting rarely covers just how large that addressable footprint actually is. Adoption, though, is genuinely hard, and it is hard for boring structural reasons rather than exciting ones. Manufacturing this kind of layered, ice-templated cement at the scale of a foundation or a load-bearing wall rather than a lab sample requires new production processes. Cost has to come down to something close to ordinary cement before a developer chooses it over the conventional version. And durability testing, years of freeze-thaw cycles, humidity, structural fatigue, has to run its full course before any building code will approve it for real construction. There is a useful historical parallel here. When carbon fiber composites first emerged as a structural material in the 1970s, the aerospace industry treated them the same way cement engineers treated conductive cement. Promising in a lab, impractical at scale. It took roughly 2 decades before carbon fiber became standard in commercial aircraft construction. The physics were never the obstacle. The manufacturing and cost curve were. Here is the closing verdict for this part of the story. The ceiling that once stood in front of energy-storing cement was technical, not theoretical. The physics has now been demonstrated and published. What remains is the unglamorous work of scaling it. The same work every transformative structural material has had to go through before it became ordinary. And if reworking concrete's internal architecture at the material level is a theme you find yourself drawn to, I already covered a related breakthrough: China's graphene concrete work, where a different Chinese research effort redesigned concrete's internal structure not for energy storage, but for raw strength. The engineering instinct behind both stories is the same one. Stop treating concrete as a finished material and start treating it as an architecture you can still design. That one is worth your time if this video held your attention. Here is the largest implication of everything you just heard. For the first time, a building material is being engineered to participate in the energy system it sits inside instead of just consuming from it. A wall that stores power is not a gadget bolted onto a structure. It is the structure quietly doing a second job it was never designed to do before. Extend that idea across an entire city, and you're no longer just talking about smarter buildings. You are talking about structures that quietly ease the load on a power grid simply by existing. No new hardware, no new footprint, just a different internal architecture inside a material that was already going to be poured regardless. If you made it this far, you now understand more about cement-based energy storage than most people who write headlines about it for a living. Here is what was actually proven. A team at Southeast University, led by Wei Lin, solved a century-old trade-off between structural strength and electrical conductivity in cement. Not with a new chemical, but with a biomimetic architecture built by freezing water on purpose. The certified result: 27.8 millisiemens per centimeter of ionic conductivity, alongside strength gains over traditional cement, was published, peer-reviewed, and stands as one of the clearest proofs yet that a wall does not have to choose between holding a roof up and holding a charge. It is worth sitting with what that cost to prove. Years spent on a problem most of the field had already filed away as unsolvable, built on an idea borrowed from a seashell rather than a chemistry lab. The wall Lin's team built still lives in a laboratory in Nanjing, not yet in anyone's house. But the physics that once said it could not be done no longer applies, and that is the part of this story that outlasts any single number. If this changed how you think about the material holding your own walls up, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. Should energy storing structural materials like this eventually be required in new construction, the same way insulation and fire codes are today? Or should something this early stay a market choice, earned rather than mandated? I read every single one. See you in the next one.